You know how graphs look like, but how do you convert it into code? Now, instead of directly telling you that this is how you store a graph, I wanted you to develop the intuition and think about it at how would you store it. So let's try doing that and let's see the different representations of the graph in terms of code. Before we move ahead, I would just like to take a moment to remind you to be consistent and make sure you do not miss any videos in the graph series. So make sure you subscribe, hit the notification bell icon. You will also stay motivated and you have no idea how much your support will mean to me. There's so much of free content available on the channel. There's HLD, LLD, DSA, Advanced C++, tutorials, mock interviews and so much more. So if you think I deserve your support, please subscribe, hit the notification bell icon. And there's obviously a bunch of stuff that I cannot do on YouTube, like mock interviews, live interactive classes. So we have educourses.com, we have live courses, self-paced courses with live doubt solving support, which both of them we have mock interviews, and we have a lot planned in LLD, HLD, Advanced C++, DSA and so much more. You have no idea. So if you want me to be part of your further learning journey process, please check it out. The link is in the description. And now let's continue. So what happens in a graph? Why is it trickier than storing the other data structures? Here the thing is that we have to represent complex relationships between different nodes, correct? So suppose if I have 5 nodes, A, B, C, D, E, A, B, C, D, E, then I have to see which all nodes are connected to which other nodes. For example, if there is, say, an edge between A and D, that means that they are directly connected. Similarly, there is an edge between D and C, that are directly connected. There is an edge between B and C, directly connected. Edge between A and D, they are directly connected. Edge between D and E, directly connected. A and B, directly connected, and so on. Now, how do I represent this in code? Basically, I have to show that every pair of nodes, I need to be able to see that for this pair, is there a direct edge or not? That is what I want to see, correct? Now, how do I store every pair of nodes? Think about it. So, if I have, say, nodes A, B, C, D, E, I want to store the information for every other node also. Think about it. They can also be a self edge, like they can be a loop that A is connected to A again or not. Maybe there's an edge like that also, correct? So, for every node, I need to see whether there is an edge to every other node, even to itself, correct? So, here I have to see is A connected to A, B, C, D, E. So, yes, this sort of looks like a 2D matrix if you think about it, right? So, if I make it look like this, so here what will happen is that I will be able to tell every node is connected to every other node or not. Now, this is one way of representation. There is one more way of representation. Let's understand this first and we will compare both the ways. And for the other representation also, I will make you think and I will make you only try to think how it should be represented in code. Okay, let's focus on this one now. So here I have made a 2D matrix, right? Now, what does each element in this 2D matrix mean? If I look at this, I want that the value over here should tell me that is there an edge between D and B or not. Similarly, the value over here will tell me is there an edge between C and D or not. The value over here will tell me is there an edge between B and E or not, and so on, correct? So basically, I want the answer in what? I want the answer in true or false, that is there an edge between this node and this node or not. So I can store it in a Boolean 2D matrix, correct? So here if we see that there is an edge between A and E. So A is connected to E, so I will put a true over here. Now note that the graph that I have drawn is an undirected graph. Remember in the last video we discussed that an undirected graph, you can also think of it as a bidirected graph. Basically, if there is an edge between A and E, you can think of it like that there is an edge from E to A also and from A to E also, right? It is bidirected. Now, it might be directed graph as well, right? So, we need to understand that how would a directed graph be different than an undirected graph in terms of representation as well. So for now, let's focus on the undirected graph, and the same thing we will also try to see in the directed graph as well. So here there is an edge between E and A. So I have put that A to E is connected. Similarly, E to A is also connected, right? Here if I say from A to B, so A to B is also connected, B to A is also connected. Similarly over here, D to A is connected, so D to E is connected. Similarly, E to D is also connected. If I come over here, D to C is connected, so D to C is connected. Similarly, C to D is also connected. If I come over here, B to C is connected, B to C is connected. Similarly, C to B is also connected. If I come over here, D to B is connected. Similarly, B to D is also connected. If I come over here, A to D is connected. Similarly, D to A is also connected. Here A to A is connected, so A to A is connected. Rest everything I can put it as false. So this graph can be represented by this 2D matrix. The 2D matrix that we just drew is called adjacency matrix. Why adjacency matrix? Firstly, obviously it is a 2D matrix, but why adjacency term? Because here we are talking about adjacent nodes. We are talking that are these two nodes adjacent nodes or not? Basically, are they neighbors or not? If you remember, in the last class we discussed that we should not be using the terms parents and children like trees over here because they can be cycles possible. So basically there is no parent and child relationship over here. Instead, they are neighbors. They are equally important sort of thing. So keep this in mind that you should be using the term adjacent nodes or neighbors in graphs. So this 2D matrix is called an adjacency matrix. And I am sure that a lot of you are already thinking about it, that in the graph like this is an undirected graph, right? In a graph like this, here you see that for every edge which connects from I to j, this is an undirected graph. So that means the edge is bidirectional. So if the value from I to j is true, then the value from j to I is also true. So in my adjacency matrix, the value at ij and the value at ji is going to be same for every value of ji, correct? So that is why the adjacency matrix for an undirected graph is going to be symmetric matrix, which means that if you take the transpose of this matrix, then you're going to end up getting the same matrix. Why is that? Because this is a bidirectional edge for every pair of nodes, correct? I hope this is like common sense. I hope you're able to visualize this. But it is not going to be true for directed graphs. For directed graph, your adjacency matrix is not going to be symmetric. You need to understand all of this. Now, in our case, we have represented as true and false. You can also represent it by 1 and 0, which you will see in a lot of places. Basically, instead of true and false, you will be writing 1, 1, 0, 1, 1. Basically, 1 instead of true and 0 instead of false. So, these are just different ways of representation. Integer obviously takes more space than a Boolean. So, I have represented it as Boolean. It takes lesser space, but you can represent as integers as well. Now, I have made a similar random graph, and now we are going to try to visualize it in a 2D matrix, which is called an adjacency matrix for this particular graph, right? So, here let's pick each edge one by one. If I pick this, so E is connected to A, right? So, I am going to put a true over here or a 1 over here. Here, if you note, here I am not putting the value for A to E also, I am just putting the value for E to A. So, instead of true and false, maybe I can put 1 and 0 also. So, right now I am putting 1 and 0, okay. Similarly, from E to D, I am putting 1. Here A to D, I am putting 1. Here A to B, I am putting 1. D to B, I am putting 1. D to C, I am putting 1. Here for B to C, I am putting 1. C to B, I am putting 1. So here if you note that for B to C, C to B, there are different edges because it is directed edge, right? So it is not like it is if B to C is connected, C to B will also be connected. There will be a different edge if there is a direct path from C to B, okay? So rest of the values, I am going to put it as 0. So this is how you can represent a directed graph in an adjacency matrix. So we have seen that how the representation is going to be different if our graph is directed or not, right? So for undirected, we saw it is going to be symmetric, and for directed, we saw it is not going to be symmetric. How will the representation be different if our graph is weighted or unweighted? What does a weighted graph mean? It means that every edge is associated with a particular weight or a cost, correct? So how would I associate that? For example, if suppose let's put some values or some cost to every edge over here. Suppose E to A value was 2. So here instead of putting E to A, instead of putting 1, I will put the weight itself. I will put the weight as 2. Correct? So basically for the pair of nodes that are not connected, the values will still be 0. But now you cannot store your matrix as true and false. You cannot store it as Boolean. You need to store it as integers or long or whatever depending on your weight or your cost. Here we need to store the cost of every edge. Suppose E to D value was say 10. So here instead of 1, I will store 10 itself. Similarly for D to C, instead of putting the value 1, suppose the cost is 5, I am going to put for D to C instead of 1, I am going to put 5. So this is how the representation will change if we have a weighted graph. We will store the weights in the matrix. The same thing will be there for undirected graph also. There can be weights in undirected graph also, right? So suppose the value over here is 10. So for E to A also, for E to A, if I see, instead of true and false, I'll have to store integers. I'll put 10 over here also, and I'll put 10 over here also, correct? Again, for an undirected graph, even if it is a weighted graph, it is going to be symmetric only, right? So undirected graph, always the matrix is going to be symmetric, but you can put weights. If it is a weighted graph, your adjacency matrix cannot be of Boolean. It has to be of integers or long values depending on the max value of the cost, but you will have to store the cost associated to every single edge. Let's talk about the amount of space that this representation takes. So suppose we have V vertices and E edges. Now sometimes you will see V being represented by N. Basically you can take any variables. Here you will always need how much space for storing this adjacency matrix? You will always need order of V square or order of N square space, correct? Now notice something very interesting. I have made one more graph over here, right? So here there are 5 nodes, and because there are 5 nodes, what will be the size of our matrix? It will be 5 by 5. So basically there are 25 elements. Here if you see how many edges I have, 1, 2, 3, 4, 5, right? A to B, B to C, C to E, D to E, and again E to A, right? So E to A, I've forgotten to mark it as 1. I'll just mark that also as 1. So here if you see, only 5 values are 1, and there are a lot of zeros over here. Can you notice a lot of zeros in this matrix? There are only 5 ones, and rest all the values are 0. It is also possible that there were only 3 edges or only 1 edge, and still you're going to end up taking 25 elements to store the entire thing. That doesn't make sense, right? You are ending up wasting a lot of space. So when are we wasting a lot of space? When our graph is what? When our graph is sparse. Remember, we talked about sparse and dense graphs in the last video. What is a sparse graph? When the number of edges is much lesser than the number of vertices. If it is a dense graph, then it is fine. There's like basically there are a lot of edges for all the pairs of vertices. So in that case, yeah, there are going to be a lot of ones, or the matrix is going to be full with values. But in a sparse graph where there are very less number of edges compared to the number of vertices, we are wasting a lot of space over here because there are going to be a lot of zeros. So is there a better way of representation if there are a lot of zeros or if the graph is sparse? Now this is an easy representation, right, because it's just a 2D matrix. Now the next representation that we are going to talk about, it is not going to be as straightforward and easy as the adjacency matrix, but it is going to be more efficient when your graphs are sparse. And we will compare all the insertion, deletion and everything in both the presentations as well. So now I wanted to think about it, that if I have only a few edges for all pairs of nodes, if I have only a few edges, is there a better way of representing the same graphs or not? If I want to use less space, now think about it. What if now I have all these nodes, right? A, B, C, D, E. What if instead of storing that for every other node is it connected or not, I just store that which all nodes is it connected to, right? Instead of storing for every other node is it connected or not, what I'm going to do now is that this node is connected to which all other nodes. Basically here if you see, A is connected to only B. So I'm going to say A is connected to B. Here B is connected to C, C is connected to D, D is connected to E, E is connected to A. So here if you see, I am not taking the other space, right? I'm not seeing what all nodes are not connected. I'm just storing the nodes that are connected. Now I know it can be a bit confusing. For now, let's take more examples and let's try to see it more clearly. Let's come back to our first example and let's try to visualize this. So this is an undirected graph. First thing that I'm going to do is put all the nodes in one place, right? So what are my number of nodes? It is V, right? So these V nodes, I've put it down in one place. Now I'm going to see this A. This A is connected to what all nodes? It is connected to A itself. It is connected to B, it is connected to D, and it is connected to E, correct? Similarly, B is connected to what? B is connected to A also. Remember, this is an undirected graph, so there are bidirectional edges. So this edge A is connected to B, so we had B in the A wala list also, and there will be A in B wala list also. So both ways it is connected, it is bidirectional, right? So B is connected to A, and it is connected to D, and it is connected to C. Your C is connected to B, and it is connected to D. Your D is connected to C, B and A, right? C, B and A. Your E is connected to A and D. So think of it like this is basically list, right? And what are the number of lists that are going to be there? There will be V lists, right? So think of it like an array of lists. So basically this is called adjacency list. So here each list shows what? Here it shows that A is connected to which other vertices, B is connected to which other vertices, C is connected to which other vertices. How many nodes are there? V nodes are there. So adjacency list is nothing but an array of lists. Don't worry about it. We are going to see the code. We are going to see so many examples of this. It will become completely clear. Let's see for the directed graph example also, and then let's compare the space complexity also and see whether we are actually improving the space complexity or not. Here also there are 5 nodes. So I will write all these nodes together, A, B, C, D, E. So the number of rows or the number of lists is going to be V only, right? Now we will see what all edges are there. So for A is connected to B, right? A is connected to B and it is connected to D. So I am going to put a list like this. Will I add E here or not? No, right? Because there is no edge from A to E. There is an edge from E to A. So this is a directed one. So I will not add E in this A wala list, correct? So here I will add B and D, that's it. In B, what are the outgoing edges? So basically there is this B to C, right? So I am adding over here. I have taken this, I have taken this, I have taken this. Is there any other edge? No. For C, there is B. So for C, there is B. Is there any other edge? No. For D, there is B, C. So for D, there is B and there is C. For E, there is A and D. A and D. So how much space is this actually taking? So firstly, there are how many lists? There are V lists, correct? And how many edges are there? So basically, how many elements will be there in total in all of these lists? There will be E, correct? So order of V plus E is the space complexity. Why again order of V plus E? See how many vertices are there? V vertices. How many connections will be there? E connections. So the space complexity becomes order of V plus E. Here in an undirected graph, the number of connections will be order of V plus 2E because bidirectional, right? So if you consider E to be the number of edges in both the directions, then it will become order of V plus E. So in general, people say order of V plus E is the space complexity. But in undirected, because it is bidirectional, it becomes order of V plus 2E. Here in adjacency matrix, the space complexity was order of V square. So now my question is always adjacency list better than adjacency matrix? Is it always more efficient or not? Think about it for a second. When I introduce adjacency list to you, what did I say? If it is a sparse matrix, if it is a sparse graph, if there are a lot of zeros, then it makes sense, correct? What is a sparse graph? When the number of edges is less than number of vertices, right? So in those cases, it makes sense. But what if? What if all the edges were connected to each other, right? So for example, let's take another example. What if I had vertices A, B, C, D, E and all of them were connected to all other vertices? So basically A is connected to B, C, D, E. B is connected to A, C, D, E. C is connected to A, B, D, E. Your D is connected to A, B, C, D. Your E is connected to A, B, C, D. So if you think about it, although the order in which I am storing is different, the way I am storing it is a bit different, still I end up taking how much space? I end up taking order of V square space. Basically 25 elements, right? Because every node is connected to every other node. Here basically it is order of V plus E only. But if you think about it, here E is your V square only, right? So it becomes order of V square. Why? Because this is a dense graph. Every node is connected to every other node. So if it is a dense graph, then you are not really doing any optimization by storing it in adjacency list. But as we discussed in the last video also, it will mostly not be mentioned in the question that it is a dense graph or a sparse graph. No question is going to mention that for you. Maybe interviewer mentions it. Then in that case, obviously adjacency list is a better way to go about it. But if your interviewer asks you that what is better, is adjacency list better or is adjacency matrix better? you need to mention it. You need to think about it. That if it is a sparse graph, if the number of edges is lesser, then adjacency list is definitely better. But if it is dense graph, if the number of edges is more only, then it really doesn't matter. Then the amount of space that you're going to take is essentially same. But basically in a dense graph, representing in a adjacency matrix is going to become much easier for you because it is easier to visualize adjacency matrix, right? And for those who are still confused about the adjacency list, it is completely fine. We're going to take a lot of examples. It will become clearer. How would you represent a weighted graph in an adjacency list? Now, this is a bit tricky, right? Because here we have the same number of nodes. So basically, if your nodes are A, B, C, D, E, here just mentioning that, okay, A is connected to B, C, D is not enough. Here you also need to store the weight or the cost associated with each edge, right? So there are two things that you need to store. One is that it is connected to which node and what is the weight or the cost of that connection or basically of that edge, correct? So you need to store two values. Suppose here A is connected to what? A is connected to B. So I'm going to store B and 6, right? So 6 is the weight. So I'm going to basically store it like this. Now you could store it like a pair of two things, or you could store it, say, a list of lists. So there are different ways of writing code, but a pair of two things, basically a pair, makes more sense, right? That what is the node and what is the weight of the edge. So that is enough, right? And visually I hope it does make sense. Similarly, if we see for the rest of it also, now A is connected to E, right? And it is 5. So E and 5. Please note that so far I have been calling my nodes as A, B, C, D, E. You could also call them as 1, 2, 3, basically anything, right? So whatever is the node called and what is the weight of the edge of the connection. Okay. Similarly, now B is connected to C and the value and the weight of the edge is 1. So C and 1. I can store it like this. Now, is C connected to anything? No, there is no outgoing edge from C, right? So this is going to be empty. There is nothing over here. There is nothing over here, right? Now D has what all outgoing edges? It has B and the weight is 3. What else is there? There is A and the weight is 7. There is A and the weight is 7. There is from E to D and the weight is 10. So this is how your adjacency list is going to look like for this matrix. Similarly, you can do for undirected graph also. The only difference is going to be that for every edge, for A to B, there is going to be the same weight, basically A to B and B to A. So if it was like this, A to B, if it was 6, you will add 6 for A to B also and you will add 6 for B to A also. I hope this makes sense. Just convert the undirected graph basically into a bidirectional graph. For every edge, I to J, connect two edges for I to J also and for J to I also. I hope you have a fair idea of both the representations of graph by now. Let's compare them a bit in detail in terms of space and the time complexities for various operations in the graph. And I hope you will be able to understand them clearly when we look at the code in future. Don't get overwhelmed right now. I understand that it can be a bit overwhelming because we are just discussing the theory. But when you look at the code, and I will be discussing the code in both C++ and Java, it will become clearer. Just stay with me for future videos also, and graphs is my responsibility. Just stick to the playlist. Okay. Starting with the space complexity, as we discussed, for adjacency matrix, it is going to be order of V square. For adjacency list, it is going to be order of V plus E. Now let's compare the time complexity for various operations that we can perform on the graph. Now, firstly, we can add or remove vertex and edge. So let's compare that. If we have to add a vertex in an adjacency matrix, what do we have to do? Add a vertex in an adjacency matrix will mean that you will have to add an entire row and entire column. Right? So if this is the adjacency matrix, if we add one more vertex, that means we are adding one row and one column, correct? So basically it is going to take you how much? It is going to take you order of V square. Versus in an adjacency list, you are not adding any edges. You are just adding, so basically these are your lists. This is one list. You're just adding one more vertex to it, but there are no edges connected to it, right? So just adding one vertex is going to take you order of 1 itself. Removing the vertex, however, in an adjacency matrix is going to be remaining same order of V square because you will be removing one row and one entire column. In an adjacency list, it is going to take you order of V plus E because when you remove a vertex, you will have to go through all the neighbors of all the nodes and see is this node connected to other nodes or not, right? Because you would have stored it in an adjacency list, would have to go through all the list and see is this node present or not, is this vertex present or not, whichever vertex you're removing. Adding an edge in both the cases, it is going to be order of 1 because you just have to add one value. In adjacency matrix, you just have to change one particular value. In adjacency list also, you just have to add to one list, so it is going to be order of 1. Now removing an edge for an adjacency matrix, it is going to be order of 1 because again you just have to change one element. But in adjacency list, it is going to be order of E. Because in the worst case, it is possible that for one node only all the edges were present, right? So there is only one node and all the edges are present, and maybe the edge that you want to remove comes at the end. So maybe it is like, so there is only one node and it is connected to all the other nodes like this. So in the worst case, you will end up going through all the edges to remove this particular edge, correct? So it will become order of E. Querying an edge, basically you have to see whether these two nodes are connected or not. Now in adjacency matrix, it is very easy, right? You just have to find matrix of ij. Versus an adjacency list, you will have to go through the entire list for that I and you will have to see is j present or not. So you will end up taking order of v max, right? Because for in the list for this ith element, so if these are your lists, for this ith element, you will have to go through all the nodes in this list, correct? What are the maximum number of nodes that are possible? Order of v. Finding neighbors is going to take us order of v in both the cases. Why? Because here also we will have to go through entire row or entire column. Here also we will have to go through one entire list, which in the worst case will be order of v. I hope the visualization and the comparison of all the complexities helped, and I hope you're liking this series. In the next video, we are finally going to get started with some algorithms and it is going to be a lot of fun. Please don't forget to subscribe so that you don't miss the videos, and please hit the notification bell icon. It will mean just so much to me. Check out Educourses, the link is in the comments, and I hope I can be part of your learning journey and I hope you will stay with me. See you next time.